Hello, welcome back to Engineering 211 Statics, and I wanted to pick up where we left off last time with equilibrium. I wanted to look at an equilibrium problem with 3 dimensions. There's those types of problems in Chapter 3. This happens to be more of a Chapter 5 problem because we'll have to use moment equations to solve it. But both chapters have 3-dimensional equilibrium problems. And I've talked about this before, but remember, if we look at the sum of the forces, that setting that equal to 0, that would give us the sum of the forces in the x is equal to 0, the sum of the forces in the y is equal to 0, and the sum of the forces in the z is equal to 0. And we then have similar equations for the moment. Sum of the moment is equal to 0 would net us the sum of the moments about the x-axis is equal to 0, sum of the moments about the y-axis is equal to 0, and sum of the moments about the z-axis is equal to 0. So with those 6 equations, we could tolerate 6 possible unknowns. So we'll keep those in mind as we go through this particular problem. So with this problem, I've got the x-axis over here, the z-axis up, the y-axis here, a little different orientation than sometimes you see, but again, a right-hand coordinate system. Going from x to y, your thumb is in the z direction. And what we have here is we have some sort of a spar pole or something that's coming out from point A. Maybe it's anchored to this wall. You could think of the side of a building or something as this plane xz, and this pole is attached at a pinned connection, or ball and socket, maybe if it's a 3-dimensional, at A, and extends out here. And then we've got a load placed on it, 850 pounds down here, and would, since this is a pinned or a ball and socket connection, we would need to have some guys supporting this. We've got a guy from point D back to E, and we have a guy from point B back to C. And both points C and E are located on the XZ plane. So I think the dimensions are given there. We're going to get to drawing the free body diagram in a little bit, but before we do that, I probably better get a handle on this force FDE. That's this one. And this force here, which is going to be, what's that, FBC. Okay, so we've got DE and we've got BC, because we're asked for the X, Y, and Z reactions at A. We'll talk about that a little more when we get to the free body diagram. And then we'd like the tension in cables BC, so that would be FBC, the tension in that cable, and the tension in DE, FDE. Well, I'm going to go ahead and use, and I'll put our general equation up here. Remember that we have that what we have, a force was equal to its magnitude times the position vector divided by the magnitude of the position vector, right? So we'll use that. I could say that FDE would be equal to the magnitude of DE, which I don't know. That's what I'm looking for. But I do know its position vector. So it's really just a matter of looking at DE, and you could take your E coordinates and subtract your D coordinates. Again, I always just think of positioning myself at D and giving myself instructions on how to get to E, or walk to E, if you will. So to do that, I would go, minus 3 in the I direction, minus 6 in the J direction, plus 2 in the K direction. Is that right? So I'd have to go, let's see, minus 6 in the Y. That's correct. And then minus 3 in the X. That's correct. And then positive 2 in the Z. So that looks correct. Now I need to divide this by the magnitude. So I'm going to divide this by 3 squared plus 6 squared plus 2 squared. I wasn't careful with the negative signs because they go away when we square it. And I think that denominator, I believe that turns out to be 7. So that'll keep the math nice and easy. We could say that this is equal to minus 3/7 FDE in the I direction, minus 6/7 FDE in the J direction, and plus 2/7 FDE in the K direction. I think that's what we've got. Let me double check my work that far. Minus 3/7, minus 6/7, and 2/7. Yes. Okay, so that's F, D, E. And we could do a very similar thing for F, what's the other one? BC, right? I could say that that was magnitude BC, which I don't know. That's what I'm looking for. But then I need to multiply this by the position vector from B. How do you get from B up to C? Well, that'd be what? 2 in the I direction, minus 3 in the J direction, plus 6 in the K direction. Is that right? So you're at B, you're going to have to go minus 3 in the Y, plus 2 in the X, and then up 6 in the Z. So I think that that is correct. And again, we would get the square root of 2 squared plus 3 squared plus 6 squared, which I think is the same thing, 7. Interestingly enough, that indicates that those two cables are the same length. Probably have drastically different forces in them, but they are the same length. So we could go through the arithmetic here then, that F, B, C is equal to 2/7 F, B, C in the I minus 3/7 F, B, C in the J plus 6/7 F, B, C in the K. Let me double check that work. 2/7 minus 3/7 and 6/7. Yeah. Okay, so we're going to hang on to those. That one right there and that one right there. Now, before I go much further, I probably need to get a free body diagram. We could have done this way back in chapter 2, so that was well before free body diagrams. But to go any further, I need to have a proper free body diagram. So let's see if I can do that. And normally with free body diagrams, we like to put in all of the dimensions and whatnot, so it's all there. Although on this one, we can end up with problems because we can get so much information. So I'm going to refer back to the original drawing for the dimensions. I'm not going to put them in here because it can just get too cluttered. But normally we like to do that. And the other thing that I'm going to do on this is I'm going to put these forces in here. So rather than just putting BC up there, I'm going to break that into the pieces. So let's see what that looks like. We've got the forces at A. A is a pin connection in 3 dimensions, so it would be like a ball in a socket. It would support a force in the X direction, the Y direction, and the Z direction. And usually in these 3D problems, I just take it in the positive X. So we've taken this as positive X. I take it in the positive Y and the positive Z. So I don't spend a lot of time trying to figure out which way these go. I just put them in positive X, positive Y, and positive Z. Let the negative signs fall where they may. Now we've got the load, 850 pounds out here. At the end of this thing, we don't necessarily have the weight of the pole itself, but I do have these forces on here. So if I look at DE, what do I have for DE? That's going to be out here in the X direction. Now I could write this as minus 3/7 in, I could put it here and I could put the arrow like that and put a minus 3/7, but I think what I will do is avoid the negative sign and I'll put the force back here. So while this term here, you can see that on the screen there, while that term there is minus 3/7, I'm going to write it as a positive 3/7 because I'm going to put it the opposite way. Okay, so I'll say that this is 3/7 FDE. Okay, so that's in the minus X direction. That's why I don't have to put the negative on it. What about the J direction, the Y direction? I have minus 6/7. So minus 6/7. The positive direction is out here. I'm going to put it like this and say that I have positive 6/7 FDE. And then the z direction, that's easy. Positive, so it's just up 2/7. So I have this one, 2/7. F, D, E. Okay, I think I'll switch pens here. Get one a little slightly sharper. Then I need to do the same thing out back here at B. At B, I'm going to look at this one. So I've got 2/7 in the X. So in the X, I will draw this like that. There is 2/7 FBC. Then I have minus 3/7. So rather than drawing it out here and putting the arrowhead on that end, I'm going to put the arrowhead on this end and get rid of the negative sign. So I have, this one is going to be 3/7. FBC. And then this Z piece is 6/7. That's another easy one that's straight up. So we have it like this. There is 6/7. Okay, so we've got 6/7 for the X, minus 3/7 for the Y. I've reversed the arrow there, so I don't need the negative sign, and 2/7. So 2/7 is this one, 6/7 is that one, 3/7 is that one. Then over here, double checking, I had the minus 3/7 and the 6/7, minus 6/7, that was that one. And there, the 2/7 is the Z. So I've placed these. I've got rid of the negative signs because I reversed the direction. Instead of saying minus 3/7 in the positive X, I've just put it as 3/7 in the negative X. And I've placed those then on this diagram. So now we have, before I run off with this sheet here, we've got our equations. We have 3 equations here. We have 3 equations there. How many unknowns do we have? Well, if I look at the unknowns, I've got FBC, I've got FDE, and then AX, AY, and AZ. So I have 5 unknowns, and we'll see what's happened to that extra equation in a moment. So why don't I start my work? I could sum the moments about the y-axis, setting that equal to 0. What do we have about the y-axis? Remember, this is the y-axis, straight out there. Everything intersects the y-axis. Everything intersects that. So there is no distance. Force times distance, the distance is 0. Everything intersects that, so we get that. That's trivial. Okay, so hopefully we don't have any more trivial equations, because I now am left with possibly 5 equations and certainly 5 unknowns. Well, let's continue on then. So if I then sum the moment about the x-axis, setting that equal to 0, what am I going to have? That's this axis here, right? So that goes down the axis. Those intersect the axis. What's going to cause a moment about the x-axis? This is not, that's not. So really all I'm going to have is this one here, 6/7 FBC. Times what distance does that act through? That acts through this distance here. I didn't put the distances on here, but we had 3, 3, and 2. So that acts through a distance of 3. Okay. And if I look at this, why don't I go ahead, I'll take this moment positive like that. So that would be positive. Then I would have to add to it this 2/7 FDE. So this one. This FDE is now acting through 6. 3 plus 3 is 6. And I don't want to forget this load out here. I'm going to have to subtract off, because that goes in the opposite direction of those two. 850 times what? 3 plus 3 plus 2 is 8. Okay, so that's a nice equation, although it has 2 unknowns. So let me go ahead and sum the moments about the z-axis. Summing the moments about the z-axis, we have a couple possibilities. Why don't I just go ahead and take this as positive? So I would have then 3/7 FDE times 6 minus, because this is going to go in the opposite direction, minus 2/7 FBC times 3. Everything else is either parallel or intersects it. So I have two nice equations, don't I? I've got this equation here. Quickly multiply both sides by 7. And you'd recognize then that, what did I have? I've got 18 FDE is equal to, because that's negative, go over to the other side, 6 FBC. So I've got that 3 FDE is equal to FBC. Well, that's a nice intermediate step, because I could substitute that back up into that equation right there, right? 3 FDE is equal to FBC. So with that then, making that substitution, I'm going to have, so I'm looking at bringing that one down and making the substitution where I have, let's see, I wrote these in slightly different order from my notes. BC, so I'm going to have 18 over 7. So 6 times 3 is 18 over 7 times FBC that we said was 3 FDE plus 12 over 7 times FDE is equal to 850 times 8. I'll check that with my notes. So I've got then 3 times 18 is 54, so I've got 12 plus 54 FDE is equal to 850 times 8 times what? I've got a 7 there too, don't I? Multiply both sides by 7. So FDE is equal to 850 times 8 times 7. That 8 didn't turn out very well, did it? 850 times 8. 850 times 8 times 7, and then I have to divide by 12 plus 54. So when you run the numbers on that, let me double check those. $721.2 pounds. I have too many significant figures there. I should just say 721, but if we're going to substitute it back in, we might want to keep that. So speaking of substituting it back in, what am I going to do with that? Well, that's going to go right back into there. So I have that FBC is equal to 3 times DE, which is 721.2, which gives me 2,164 pounds. Okay, 2,164, is that right? Yeah. So we found the tension in cables BC and DE. Good. And while they were the same length, they had drastically different amounts of load in them. So now we're looking for AX, AY, and AZ. As far as keeping track of the equations, we've used all of our moment equations up, so let's move on and look at the force equations. So I'll continue to come back to this free body diagram. So with the looking at that free body diagram there, I need to write my force equations, don't I? So I could say that the sum of the forces in the x is equal to 0, and I'll just go ahead and take positive x. Which way is positive x there? There's positive x, so I'm looking at that as positive. There's positive x. So I could say that I have ax plus 2/7 FBC minus 3/7 FDE. Anything else in the x direction? No, I think that's it. So I've got then that AX is equal to 3/7 FDE. Did we have FDE? Right there. That's the 721 minus 2/7 FBC. That was the 2164. That's a 2, not a decimal. 2164. Which should give us a value of minus 309. Let me double check that real quick. Yes, 309. So it looks like our AX, we had assumed it that direction, and the real direction is back there. That's okay. I would have had a hard time telling that from the beginning, so I just put this in the positive direction, let the negative signs fall where they may. Well, let's continue on with this. What if we sum the forces in the y direction, setting them equal to 0? The y direction, that's straight through down that pole. So we'll take that as positive, and we're going to have then AY. What else are we going to have? Minus 3/7 FBC, minus 3/7 because it's going up there, which I would have had that negative if I just would have followed through with minus 3/7 FBC right there. See, there's that negative right there. It worked out. Okay, FBC. And this one's going to be negative 2, minus 6/7 FDE. I don't have any other loads, so those are the only three in the y direction. So I can say that AY is equal to 3/7 BC, which is what? Let's see, 3/7. 3/7, where is BC? BC 2164. That turns to positive. That goes to positive also. 6/7 DE 721. Making that substitution. So that should turn out to be 1545 pounds. Let me double check that. Yep, 1545 pounds. And we'll talk more about that. That's an important answer. But let me finish up while we're here. Sum of the forces in the z direction is equal to 0. What do we take as a positive z? We've taken up as positive z. We'll take that positive. And what do I have? I have az and then that's positive, so plus 6/7 FBC, and then this one plus 2/7 FDE. So 6/7, 2/7, and then I don't want to forget this load. Sometimes we don't use it for a while and then we forget about it, but that's acting down, minus 850. So I should be able to then say that AZ is equal to 850 minus 6/7 FBC. BC, that's 2164 minus 2/7 FDE. DE, 721, which turns out to be equal to minus 1,211 pounds. And I'll double check that too. Yeah, 1,210.85 minus 1,211 pounds. Good. Okay. So, like I said, these answers are important because if we come back and we look at this free body diagram here, it's telling me that this AY right here, this AY is a positive. I mean, these two are negative. It just means I got the answer wrong. I know that the X is in that direction. The Z is really going to be in that direction. That would have been very hard to figure out from at the beginning. The Y we happen to get right. And this is an important number because if you go back to the original problem, 1545, what does that force in the Y direction represent? Really, that's the force there where I said if this was some brick wall and we were coming up with putting a kind of a temporary crane or something on it, that's the force that's trying to push a hole in that wall, 1545. So that would be good for design. Maybe we'd have to come in and we'd have to put some sort of a reinforcing plate in there. You don't want to punch the crane post right through the brick or something like that. So these numbers, while we don't want to get lost in them with all the tedium and whatnot, they're very important. Okay, and speaking of tedium, I don't know that we would say that this process is all that difficult. We again drew a free body diagram. We used our equations. It is very tedious. It requires good record keeping. It can be kind of long, but really nothing new. You draw your free body diagram, you write your equilibrium equations, and the problem pops out just like the two-dimensional problems. Well, that's our three-dimensional problem. I think when we get together next time, we'll move into Chapter 6, which deals with trusses. And again, that's really just a special form of equilibrium. We'll get to use method of joints and method of sections as we go forward with that. So this is really finishing up the material that we've been doing in Chapter 3 and Chapter 5. So tackle those homework questions and make sure that you're comfortable with equilibrium, because drawing free body diagrams and using your equilibrium equations is really the heart of statics. And you'll see that again in Chapter 6 and then Chapter 7. As we just do those techniques over and over again to answer questions. And we'll talk about frames and machines and give them special names, but really what we're doing is we are doing equilibrium problems. So thank you for watching and take care till then.